Okay guys, in this video we are going to be talking about the strengths of ionic and covalent bonds. We will start with covalent bonds first. The term bond dissociation energy refers to the amount of energy that's required to break a covalent bond. Recall that whenever you break a bond, it's always an endothermic process, and it doesn't matter whether it's covalent or ionic, or if it's an intermolecular bond, which we'll talk about later in the course. Whenever you break a bond, it's always an endothermic process. So here we have some hypothetical diatomic compound XY. If you break the covalent bond between those two atoms, the enthalpy change is going to be positive. More or less, we can equate that enthalpy change with the bond dissociation energy, which in these notes is represented by the symbol D. Here's a practical example involving the dissociation of diatomic hydrogen. Whenever you break diatomic hydrogen, the enthalpy change is 436 kilojoules per mole, and that's what we're calling the bond dissociation energy. Here's another example involving a polyatomic molecule. This is methane. Methane has 4 carbon-hydrogen bonds. Let's suppose that we broke all of those bonds and measured the enthalpy of that reaction. We get 1660. We would take the average carbon-hydrogen bond to be 1/4 of that number. Since we break 4 carbon-hydrogen bonds, we would divide that number by 4 to get the average carbon-hydrogen bond dissociation energy. There's a couple of trends to keep in mind for covalent bonds. There's a relationship between the bond order of a covalent bond, that is whether it's a single, double, or triple bond, and the bond length. And what we find is that single bonds are longer than double bonds, and double bonds are longer than triple bonds. So triple bonds are the shortest, single bonds are the longest. For the bond strength with respect to bond order, single bonds are weaker than double bonds, and double bonds are weaker than triple bonds. So triple bonds are the strongest, single bonds are the weakest. And this example problem right here asks us to explore that, to put those rules into practice for several molecules containing a nitrogen-nitrogen bond. Okay, so we'll take a look at into H4. I won't derive the full Lewis structure for you, but I will show it to you. So here you're going to have a single bond, and then you'll have each nitrogen is covalently bonded to 2 hydrogens. For N2, we've looked at N2 before. N2 has a triple bond. And then in this last example, this last molecule, into H2 will have a double bond, and then each of those are bonded to two hydrogens. So which of these molecules has the shortest nitrogen-nitrogen bond? That would be the nitrogen diatom. So this one would be the shortest. Which one would be the longest? That would be the single bond. Which one has the weakest nitrogen-nitrogen bond? That would be the single bond. And which one would be the strongest? The triple bond. The double bond would be in between with respect to both length and strength. Well, in this next topic, we're going to discuss a way of estimating the enthalpy of reaction using a table of bond energies. So again, we've got the rules there. Bond breaking is endothermic. Bond forming is exothermic. You can use this as a strategy to estimate the enthalpy change for a chemical reaction. And the way we do that is we use this formula here, which I'll ask you to remember as bonds broken minus bonds formed. So what you want to do for your reactants you want to add up all of the bond energies for all of the bonds that are broken in the reactants, and then you subtract from that the sum of the bond energies for all of the bonds that are formed in the products. And that gives you a way of estimating delta H. Now this is not going to be an accurate value for delta H. And the reason for that is because these dissociation energies, or these bond enthalpies, whichever you want to call them, they are not precise quantities. They are averaged over many different compounds. Okay, and so it's not the same thing as what we did before in thermochemistry when we calculated enthalpies of reaction from enthalpies of formation. This is more of a best guess in a sense. Anyway, I'm going to show you how to put this into practice. And so this is the problem that we were looking at before. We have methane here, and we're being asked to estimate the bond dissociation energy from the enthalpy of reaction. And the way that we would use this formula, okay, we would say that the delta H of reaction, it's going to be equal to approximately equal to the number of bonds broken in the reactants. And so there are 4 carbon-hydrogen bonds that are being broken. So we'll say 4 times dCH, where dCH represents the bond enthalpy that we're trying to calculate, minus the bond dissociation energies for the bonds that are formed. And there's none being formed in the products, right? It's just atoms, and so that term's going to be 0. We know the delta H, so we can calculate the dissociation energy for methane. We'll take that 1662 kilojoules. That's probably kilojoules per mole, actually. And we'll divide it by 4, and that'll give us the number that they want. So I'm getting around 415 kilojoules per mole. So that's the average carbon-hydrogen bond energy in methane. Here's another example for us to look at. So here we've got a chemical reaction, and what's listed here below the chemical reaction, these are the bond enthalpies for the various bonds that we need to consider. And so you want to remember it's bonds broken minus bonds formed. Bonds broken in the reactants minus the bonds that are formed in the products. And so I'm just going to break every bond in the reactants. So we've got 4. Well, let me back up a step. What you need to be able to do first is figure out what chemical bonds do you have. I often skip that step. We've got methane, so you need to work out the Lewis structure for methane. And then you need to know that there's a single bond for chlorine. And then in the products, you'd need to come up with this Lewis structure here for the first product, and then plus HCl. Okay, so now we can see what bonds we have. I'm going to break every bond in the reactants, and then I'm going to reform every bond in the products. So our delta H, we're going to break the 4 carbon-hydrogen bonds. So I'm going to say 4 times the dissociation energy for a carbon-hydrogen bond, and then plus the dissociation energy for the chlorine-chlorine bond. And now I'm going to start subtracting off the bond energies for the products. Okay, so minus, looks like I'm making 3 carbon-hydrogen bonds. And I just made 1 carbon-chlorine bond. And then we also have formed an a hydrogen-chlorine bond as well. So I'm going to subtract that off too. Okay. So now we will use the numbers from the table. So we'll have 4 times 413 plus 242 minus 3 times 413 minus 328 minus 431. So I just pulled, for all of these bonds that I was breaking or forming, I just pulled the numbers from the table, and then we run it through our calculator. And if I did that correctly, you get something like minus 104 kilojoules per mole. It's useful to check these types of calculations twice just to make sure you get the correct number. I think that's the correct number, but I could be wrong. You check it for me, see if I got it right. This is how you calculate, or estimate, I should say, enthalpies of reaction from bond dissociation energies. Here's another one for you guys to try out. What I will do, just to take some of the guesswork out of it, I'm going to write out the Lewis structures, and then you should be able to do the calculation from there. So let me do the Lewis structures first. You should be able to get those too, but I just want to make sure that you start with the right Lewis structures. So this would be the structure for ethylene. That's the first reactant. And then you've got, don't forget about the 3 here, 3 oxygens with the double bond. And then for the products, you're going to have 2 carbon dioxides. Don't forget about the 2 there. And then the other product, you've got the 2 waters. And when you calculate the number of oxygen double bonds that are broken, right, it's not just 1 oxygen double bond that's broken, it's 3 times that. And when you calculate the number of carbon-oxygen double bonds that form, it's not just 2, it's 2 times 2 equals 4, right? There are 4 carbon-oxygen double bonds being formed. So don't forget about the stoichiometric coefficients in front. If you put those in, then you'll get the correct answer. I'm going to leave this one as an exercise for you guys to try. Well, in this next topic, we're going to turn to the subject of ionic compounds, and we're going to discuss what's called the lattice energy. So the lattice energy of an ionic compound is the energy required to take the solid ionic compound and to separate it into its gaseous ions. So here M represents some metal cation, and the X represents some nonmetal anion. Okay, so here we have the ionic compound in the solid state in its crystalline form, and then the products are the ions that make up that crystal, but in their gaseous state. Okay, so the enthalpy change for this reaction is called the lattice energy, and you are breaking ionic bonds in this reaction, and so this is an endothermic process. Again, it's very important to understand this concept. Whenever you break a bond, covalent or ionic, it's always endothermic. The lattice energy depends upon the characteristics of the ion. In particular, it depends upon the ion charges. So Z plus here, this represents the charge, the magnitude of the charge on the cation, and Z minus represents the magnitude of the charge on the anion. Okay, so the lattice energy increases with the magnitude of the charges on the ions. The larger the charges, the more difficult it is to break those ionic bonds. It's also inversely proportional to the distance between the ions in the crystal. Okay, so as the distance between the ions in the crystal gets larger and larger, for example, if you have larger ions, then the lattice energy will decrease. So this distance between the ions, that number depends upon the size of the ions. So the lattice energy increases with ion charge, and it decreases with ion size. Okay, so that's the takeaway from this formula here. It's not something that you're going to have to use to do calculations, but there's important concepts in here. The quantity C out in front is just a proportionality factor, and so this depends upon what crystal you're talking about. So we don't really need to worry about the value of C. Like I said, we're not going to do any calculations directly with this formula. You will have to do little conceptual problems like this one. So here we're comparing aluminum oxide to aluminum selenide, and we're being asked to determine which of these two species has the larger lattice energy. And so here's how you want to think about part A. Okay, so you've got aluminum oxide and aluminum selenide. Well, aluminum is common to both of them, okay? And aluminum has a +3 charge. Sorry about that. Selenide like that, not selenate or selenite, but selenide. The oxygen has a -2 charge, and if you look on the periodic table, let me pull that back up, you'll see selenium also has a -2 charge. Okay, so the cations and the anions in these two ionic compounds, they have the same charges. So it's not the charges that make the difference. It's going to be the size of the ions. Aluminum is the same size in both. However, selenium, the selenide ion, is going to be a much larger ion than the oxygen. Okay? Now, because the selenide is a larger ion than oxide, it means that the cations are further away from the selenide ions. Okay? And the interaction between the ions is going to be weaker. As a consequence of that, the lattice energy is going to be smaller for the aluminum selenide than it will be for the aluminum oxide. Because the oxide ions are smaller, they can get closer to the aluminum ions, and the interaction between the cations and the anions are going to be larger. Therefore, it's going to be more difficult to take the solid and blow it up and turn it into ions. Okay, so if we were to rank the lattice energy, we would say that the aluminum selenide has a smaller lattice energy than the aluminum oxide. For part B, we're comparing zinc oxide to sodium chloride. Zinc is a +2 cation, oxygen is a -2 cation. Sodium is a +1, chlorine is a -1 cation. Okay, so the magnitude of the charges are much smaller, or they're different between these two compounds. And the distance between the ions is hard to estimate, really. If you look at, zinc and oxygen, okay, you've got one ion in group 2, the other one's in group 4. For sodium chloride, okay, both ions are in group 3. And so it's kind of a wash in terms of the distance between the ions. You really can't say for certain without going to actual data. What I'm going to tell you here is that the bond distance is not very important in this problem, right? Because here I would say that since you really can't tell the difference, what we should focus on is the charges. The magnitude of the charges in the zinc oxide is much larger than it is in the sodium chloride. Therefore, the interaction between zinc and oxygen and the zinc and oxygen ions is going to be larger in zinc oxide. Therefore, it's going to have a larger lattice energy. So in terms of ranking these, we would say that the sodium chloride has a smaller lattice energy compared to the zinc oxide. Okay, the charges are what are important in this part. Well, I have one more topic for this video. It's kind of a complicated one, but let's take a look at it. So it deals with lattice energies, and lattice energies can be determined from the so-called Born-Haber cycle. Okay, it turns out that you can't carry out that reaction directly. Let me show you again. These types of reactions, where you take an ionic crystal and blow it up into its ions, you can't actually carry that reaction out and accurately measure the delta H. So it's difficult to determine lattice energies experimentally. What you can do, however, is take advantage of Hess's law and use what's called the Born-Haber cycle. Okay? What the Born-Haber cycle does is it allows you to calculate the lattice energy from other reactions that are known. For example, the enthalpy of formation of the ionic compound, and the sublimation enthalpy of the metal for the cation, and the ionization energy of that cation, and if there's any dissociation energies that you need to know, and likely the electron affinity of the nonmetal atom which forms the anion. Okay, so using these known reactions and the Born-Haber cycle, you can determine the lattice energy of an ionic compound. And so I'm going to illustrate that for this cesium fluoride lattice energy. So we desire to calculate the lattice energy for cesium fluoride, and we're going to use these known reactions. So the enthalpy of formation for cesium fluoride is known, the sublimation enthalpy of cesium is known, the ionization energy of cesium is known, the dissociation energy of fluorine is known, and the electron affinity of fluorine is known. So the question is how to combine these reactions in such a way that you can construct this reaction here involving the lattice energy. Well, let me show you how it works. It's a little tricky, but I'm going to take you through it. Okay, so we're going to start with the elements. We're going to start with cesium solid, and we'll start with diatomic fluorine. Okay, and what we're going to do first is we're going to convert the metal to its gaseous state. Okay, and that involves a sublimation reaction. So that's going to take us to the gaseous state of the metallic cesium, and we've left the fluorine alone so far. Now let's go ahead and dissociate the fluorine. Okay, so we're going to take the fluorine molecule and we're going to dissociate the bond. So now we have a fluorine atom in the gaseous state. Next, what we'll do is we're going to form the cesium cation. Okay, so we are going to ionize the cesium. So that's going to involve the ionization energy. So cesium plus an electron, plus that neutral fluorine that we haven't done anything with just yet. Now what we'll do is we'll capture that electron, which is what the electron affinity involves. So we're going to make cesium plus gaseous state plus the fluoride ion. Notice that's what we want, right? We're trying to get at the lattice energy, and these are the products of the lattice energy reaction. So in the last step, what we're going to do, and I should have written down, this is the electron affinity of fluorine here, this energy difference between them. Next, what we're going to do, lastly, what we'll do is we will form the crystal from the gaseous ions. And this is the reverse of the reaction that we want, right? We have, in the reaction that we want the ionic compound going to the ions. What we've constructed here is the reverse of that. So this energy difference is minus the lattice energy. And now here comes the what you have to realize is that the beginning of this big cycle that we're making and the end of it, this is the formation reaction that we talked about in thermochemistry. Okay, so we know this leg of the cycle, and we know every single other step except for the lattice energy. So we have two paths to get from here to there, and they are connected by Hess's law. And so what we can say is that this path here, the enthalpy of formation, will be equal to all of these other steps. So the enthalpy of sublimation, the dissociation energy, the ionization energy, the electron affinity. We add all of those up minus the lattice energy. Mathematically, this is true. And so what we'll do is we'll use this equation to solve for the lattice energy. Okay, it's easy to do. And then we know all of these quantities, and so we just have to do the calculation. I'm going to let you work that out on your own. But this is how the Born-Haber cycle works. You need to figure out what the lattice energy is using these known reactions. And so now it's just a matter of substituting in the numbers to get the final answer for the lattice energy. Okay, so I am going to stop this video right here, and in the next one we'll talk about molecular geometry.